Okay, that's good. طيب. If I want to read what we have seen last time, so last time we have seen first the different steps needed to fabricate the integrated circuit, and we mentioned that we have something called masks, and we need to use the mask as one step of the photolithography. And the photolithography the photolithography in general helps in order to specify the region needed to be doped or needed to be deposit any layers of the material. We have seen also last time what are different masks. For example, if we need to fabricate a simple inverter like this one here, we have seen that, for example, we need here to have 6 masks. The mask here are polysilicon mask, metal. You have also N plus, P plus, N plus, contact, and finally we have also N1. So here are the different masks that we need to in order to fabricate the inverter. Here you can see here a cross-section view of the inverter. So what I mean cross-section view, I mean if I take here, so this is called layout. No, this is called layout. This is a layout for the inverter. Type. If I ask you now to sketch, let me ask you here. If I ask you here, who can sketch layout for, I need a layout for NMOS, simple layout for NMOS. Who can do it? And I need here simple layout for PMOS. Who can do it? So here, as I said, I need layout. And here also I need layout for PMOS. Come on, it's too easy. Very simple layout. I did it a lot. Okay, Taiba. Yalla ya Taiba. No, this is not Taiba. This is the symbol of the MOSFET. I need the layout. So this is a schematic circuit. What you are sketching here is a schematic circuit of the layout. What I need here, I need the layout of the MOSFET. Yes, correct, Adil. Anyone can do it? No? هتزعلوني هيك. يلا عادل. But what do you have on the in general? Let's see, Adil. Adil, I think what you are sketching here is the cross-section view. And you are sketching the cross-section view, and if you mean here you have N plus and here you have N plus, this is what you have? Yeah, no, this is the cross-section view. This is not the layout. The layout, what you can see from the top. So if you are checking your circuit from the top, what you can see, this is the layout of the integrated circuit or of the device, whatever. So let me try to sketch it here very quickly. Well, if you want to check the NMOS, for the NMOS you have N plus and you have polysilicon. I already sketched this part many times. So here you have N plus. This is the N plus active region. And this one here is the poly. Okay, so here I have the poly, and this layer here is N plus. Well, this is the simplest NMOS you can have. If you need more detail here, of course, you have to add here the contacts here and one contact here at least. You should have also, for example, the metal. So I need to connect the drain to the outside. I need to connect the source to the outside. Also, it will be good if I add here a contact to connect the gate, of course, with metal for the gate. Of course, here, if you need to sketch more detail, you have to sketch here the P plus to connect the body of the MOSFET. So this is the layout. Is it clear, guys? This one is called layout. When you sketch the mask, when you sketch the different mask on the top to each other, this is the layout. Type now, what is the layout for PMOS? What do you have more in case of PMOS? In case of PMOS, we have to add what? First, we should have NWell, and the PMOS will be inside. Come on. I don't know why my pen is not working. So inside the NWell, we have here the P plus layer, and also we have the polysilicon. So this one is the poly. Is it clear, guys? Okay. Let's go back now to our circuit. So please try to focus, try to pay attention to my explanation. So here is the layout, as I mentioned before. You can see the different layers of the material. We have layer for the polysilicon, N plus, P plus, N well, and so on. If I continue here, so this is called cross-sectional view. Okay, what you can see here, this form here is called cross-sectional view. What I have here is the layout. What I have here is the cross-sectional view. That means if I take here the wafer, I cut this wafer along this line here, and I check what I can see. In this case, I can see this form here. This is the cross-sectional view. Did you understand now the difference between cross-sectional view, layout, and schematic circuit? Here, this one is called, schematic circuit. The circuit with the symbols, with everything is called schematic circuit. Here, I have the layout. And here I have the cross-sectional view. I hope it's clear now for everybody. Last time we stopped here when we were explaining what is the design rule and what is the meaning of the design rule. Of course, if you are working in some technologies, you cannot do whatever you want in the layout and you say, okay, it will work. No, you have always some rules should be respected. In general, the rules are defined in terms of lambda. What is lambda? Lambda in general is the half of the minimum permitted gate length. What I mean by that? Yani, if, for example, I'm working on 0.8 micrometer technology, what that means? When I say 0.8 micrometer technology, what I mean by that? I need an answer. The size of what, ya Adil? This, when I say 0.8 micrometer technology, so this is the minimum permitted gate or channel length. Yani the minimum allowed channel length in this technology is 0.8 micrometer. I cannot have a channel length smaller than 0.8 micrometer. I can have one higher, but not lower. Okay, is it clear? So they defined lambda as half of the minimum permitted gate length. So if I'm working on 0.8 micrometer technology, that means here lambda equals what? In this case, lambda equals 0.4 micrometer. Let's have an example here. The minimum distance, for example, between the contact and the edge of the N plus. So for your information, just to know, this layer here is N plus. The squared here is the contact. Then you have this layer here, the dark brown here is dark gray here is the polysilicon. So the minimum distance between the edge of the contact and the edge of the N plus is equal to lambda. The minimum width of the N plus region is 4 lambda. The minimum size of the contact, which is always squared, it's equal to what? To 2 lambda. The minimum distance between the contact and the polysilicon equals to lambda. Well, you don't need to memorize all of them, but what you have to do here, what you have to know here, you have to know that there are some rules, and these rules should be respected. Is that clear? These rules should be respected. Type. What about if the relation, some students always make relation between this slide and this slide here, which is not correct. Something else which is called mask misalignment. What is the meaning of mask misalignment? If I have, for example, I want to have a whatever, I want to fabricate the inverter, let's say that. So I have here my wafer, and the mask will be here. Let's say this is the mask for the first layer, which was N-well. So this is the mask for N-well. Type. The mask N of N-well should be only here. But always they add some crosses in the different places to the mask. Why? Because when we are going to do the next mask, we should have all the crosses on the top to each other. And now I finished the N-well mask. I prepared it. Then I have to move to the second mask, which was, for example, N plus. So in this case, so I will remove here the N-well. But now in my circuit, in my wafer, I have the crosses already printed. Later on, when I want to apply another mask, for example, the mask for the N plus, so the mask for the N plus will be here. And I should have the same crosses on the N plus mask, and the crosses should be always here on the top of the first crosses to be sure that I'm putting the mask in the correct place. If not, I will have some move or some shift. Okay, so here for example, here I have N plus, I have N plus here and N plus here. If I didn't put the crosses in the correct place, I will have some shift, so the N plus will not be in its correct place. And here we have a problem. Well, once I don't have my so this is called mask misalignment. What is the problem here? Correct place. We can see that the contact, they are shifted a little bit to the right, صح? Meaning they should be here, but they are shifted a little bit to the right. And if we check the circuit here, if we are doing the same one here, this mask, this contact here is shifted a little bit. So this is because of the mask misalignment. And also, we should have the polysilicon here. It's also shifted a little bit to the top. So here we have two mask misalignment. One for the one is for the polysilicon and the second is for the contact. Correct? طيب, what is the problem because of this mask misalignment? What is the problem here? Can you tell me that in this case, or can can you see that the MOSFET here can work correctly? Yes or no? No. Why no? Because we can see here the N plus of the drain is connected to the N plus of the source. So here we don't need a channel to contact the current, The current can flow directly. And if I want to sketch here the schematic of the NMOS, it's clear for me that the drain is connected to the source. The drain is connected to the source. I have short circuit here between the drain and the source. What else? Can you see another problem here? Also, I can see that the contact is on the top of the polysilicon. So in this case, like the source region is connected or is short-circuited to the gate region. So I have here another short circuit. I don't have here a MOSFET. I have just a short circuit between the point here, and the point here. So always if we are doing the photolithography, we have to be sure that the mask is posted in its correct place. Well, currently, and the big industry is currently, in general, everything is automated. But if you are working in some lab and you need to do you are doing some research, you need to check if this technology is working or not. So you have to do everything manually. As I did, for example, in my PhD, in my postdoc, we are doing everything manually. So you have to be sure always that the mask is posted in its correct place. Any question regarding the mask mix alignment? Okay. So let's see here. If I want to check now the layout here. If I want to check the If I want to check the layout here, what you can see. Well, be sure that you will have similar question on the in-class assignment. So if you have, I will repeat my question. If you have similar layout, or if you have a layout like this one, what you can see in this layout? Everybody is following me. It's very important. This part is very important. So please try to focus. Try to ask if you have some part is not clear. Let me start with Zahra. Zahra is here. No. Taiba Yasin. Taiba is here. Saud Lanizi. Saud. Sarah Rashidi. Is Sarah here? Yes. Ruqayya Jakhir. Is Ruqayya here? Yes. Reem Muhammad. Reem. Okay. Monica Wahib. Okay, Monica. Hussein Al-Amir. Hussein. Okay, Zahra. So Hussein is here. Haya Zwayed. Okay. Ghadir Bou Abbas. Ghadir Bou Abbas.
Yes.
Okay, Ghadir. Abdul Aziz Al-Gaoud. Okay, Adil Jamal. Adil Jamal. Okay, Badr Al-Aswad. دلال السلطان. دانا الفوزان. اوكي دلال. اوكي دانا. ديما الهدية. اوكي ديما. عيسى الكندري. اوكي عيسى حسن. عيسى حسن. فجر. اوكي فجر. So here I have Isa Hassan and Saud Lanizi are not here. وين كنت يا سعود؟ Isa also. Okay, let's go back to the circuit here. Did you get some idea about what do you have here as devices? Let me give you some sign. Okay, when I asked you to sketch the layout of the NMOS, I told you that the NMOS is like that. The most simple layout of the NMOS. صح? Here you have N plus, here N plus, and here is polysilicon. Is that correct? So always, if you see N plus, then poly, then N plus, that means you have MOSFET. Okay? If you see N plus, polysilicon, N plus, that means you have NMOS. How to sketch it? Well, I know this N plus could be drain or source, correct? Then I have the polysilicon. The polysilicon is always the gate. So drain or source, gate, then drain or source. Here is the layout. Here is the schematic circuit of this layout. Okay, by this way we can find or we can extract the schematic circuit. Let's do that here. And the one here, do we have MOSFET? Do you have NMOS? Can you see NMOS in this layout? Guys, please, I need some interaction to be sure that everything is working well. Is everything okay? You are not facing problem. Don't need me to focus on some points you are not understanding it. Please, I need more interaction in the class. Can you see here MOSFET? Can you see here N plus, poly N plus? Let me help you. This white gray here is N plus. These squared here are contacts. Then the two dark gray here, they are polysilicon. Now, can you see MOSFETs in the layout here? Type. How many MOSFETs and how they are connected? How many MOSFETs you can see here in the circuit or in this layout? In this case, look, as I mentioned, source. Then once you have poly, you sketch the gate. صح? This is what we have decided here. Type. Let's move now to the layout. Here I have drain or source. Let me increase the size of the line so you can see it better. So I didn't get your question, ya Dalal. Yes, it means a gate. So once I have a poly between two N plus region, so this poly is the gate of the MOSFET. once you have n plus, not n most, n plus, like here, here, and here, so that means you have drain or source. So here, for example, I have n plus, so I sketched here drain or source. I don't know, and they didn't tell me what is this region, if is it n or if is it source or drain. They didn't mention, so also I will not mention here. Okay, Dalal, is that clear now? Here also I have n plus, so I will sketch drain or source. Then I have here the polysilicon, that means here I have a gate. Another n plus, so also drain or source. Then another poly, another gate, and finally another n plus. If I want to sketch the circuit, so I can say that n MOSes, they are connected in series, and two gates here. I don't know the gates connected to what. I don't know here it's connected to what because they did not mention. I don't know also this terminal is connected to what because also mentioned. Did you understand now how I extract the schematic circuit here from the layout? For everybody? Type. Now we move to a second part. And this part, well, everyone has its method. Well, for me, I have to see poly, but this poly should be from the first side I have n plus, and from the second side I have n plus. P plus here and the P plus here and poly in the middle. I have to be sure that all of them are in N well. If they are not in N well, that means I don't have PMOS. Once I see that they are in N well, so I can know that this is a PMOS. Okay, Monica? Well, if from your method, of the method you prefer that you have to check if you have poly or not, also okay. But this poly should be encountered from two sides by N plus or P plus. Type. Now we, from the beginning of this course, we were focusing on checking the internal capacitance of all the devices. And we started with the diode, then we moved to the MOSFET, and we talked a lot about the calculation of the different capacitances. Is that correct? So the calculation of the capacitance is very interesting. And if you want to talk about the capacitance of the junction, and for example, you know it's a junction capacitance, صح? And here is P, here is drain, you have here N plus, here is P. We have a capacitance between the drain and the body, and this capacitance is a junction capacitance. And you know that if I need to calculate the total capacitance here, it will be multiplied by the area of this junction. So always I have the capacitance is proportional to the area. You have seen that in the diode, and also we have seen it in the MOSFET, correct? So always I have the capacitance, the junction capacitance is proportional to the area. Type here, I have three junctions. You will tell me, doctor, why you call it here junction? Why you said that here I have J1, G2, G3, why you called them junction? I call them junction because let's say I need to sketch the cross-sectional view along this line. What I can see. Now you know what I mean by cross-sectional view, صح? If I need to sketch the cross-sectional view, I have to start always with the substrate. Let me just here have some space. So I will start always with a substrate. What I'm doing here, cross sectional view along x prime x. So here is x prime and here is x. What I can see now here, I start from here, from the left. From the left, what I crossed here, the first thing I crossed is what? N plus, correct? So I start from here with N plus. I have N plus from here until here. Type N plus is under the surface or on the top of the surface? Plus is inside the silicon wafer or on the top of the silicon wafer? It's inside, correct? So here I have N plus. N plus from here to here. Then starting from this point to this point, I have what here? From here to here, what I have? I have poly on the top, correct? So I have poly on the top. And always, if you have polysilicon, so you should sketch the silicon oxide layer. If you did not sketch the silicon oxide layer, lose some grades, some points. Type. Then I have another N plus from here to here, another N plus from here to here, another poly from here to here, another polysilicon oxide, of course. Then from here to here, I have what? I have N plus. Everybody understood the cross-section view? Of course, here I have to mention that this one is a P minus substrate. Type. Did I finish? Or there is something I didn't sketched here? What do you think? Yes, correct. The contact. I should sketch the contact here. Of course, here I prefer, if you are doing that in the assignment, to change the colors, okay? So here I have a contact from this point to this point, so approximately like that. So always you can sketch the contact like a pillar. This is the contact, and you have to mention that here I have the contact, here I have polysilicon, here I have silicon oxide, and so on. As I said, cross-section view means I cutted the wafer here and I checked what I can see. Okay, Dalal? Let's go back to the story of the cookies. Understand here. During the first lecture, I told you when I was explaining the cross-section view, I told you, let's say, for example, you have a cookie, and in this cookie, you have here one resin. You have also here one piece of dark chocolate, and you have here one piece of pistachios. Okay, Dalal? And also here, let me say that, just to answer your question, ya Dalal, let's say here I have another piece of chocolate. So I have here two pieces of chocolate. I have one piece of resin and one piece of... Now, if I cut this wafer or this one along this line, what I can see? What I can see here? Of course, what I can see, well, first I will sketch the form of the cookie, which is like that. So, from the beginning here, I can see the resin here. Is that correct? Can I see something else? No, because nothing here. But if I cutted this this wafer or this cookie along this line here, like that, what I can see? I will sketch here the cookie like that. So I have to mention here that I have one chocolate here, and one chocolate here. let's go back to our circuit here, to our layout. I have n plus from this point to this point. Another n plus from this point. I'm talking about this line. I cut the wafer along this line. I have n plus from here to here, from here to here, and from here to here. Is it clear for everybody now? Why 3 n plus? You have to know that this layer n plus, is taken the whole area. This layer n plus is taken the whole area. But why I didn't sketch here n plus if it's taken the whole area? Because once I have polysilicon, the polysilicon neglect the effect of n plus or make the region not active. So this n plus will be removed. Okay, guys? So the the polysilicon neglect the effect of the active region or make the region non-active. Is it clear? Let's go back now to my question. Why they call it here junction? Because if I'm talking about this region from here to here, it consists of a junction between n plus and p. So here, this is the junction J1, and the junction from here to here is the junction J3, and from here to here I have the junction J2. Okay, guys? Is it clear now? Why I call it a junction? Because it consists of a junction between, for example, here n plus and p, here I have n plus and p, and here I have n plus and p. Here I have 3 junctions, so I have to talk about 3 junctions here. Type. Let's move now to the next step. As mentioned before, that the different capacitances, junction capacitances, they are proportional to the area. And some of the capacities on the edges here, if you remember, we had some capacitances on the edges. If you remember, it was CSSW and CDSW. Here we have P plus field implement, and this capacitance in general is proportional to the perimeter of this P plus field implant. So now you have to know how to calculate the area of the junction and the perimeter of the junction. You know, I think, how to calculate the area of the junction. If you have a junction like that, how to calculate the area? Well, if this one is the width, this one is the length, so the area in this case equals the width multiplied by the length, correct? Regarding the perimeter, well, the perimeter here, as I said, it's needed to calculate some capacitances. And these capacitances exist only here, here, and here. They are not exist in the channel side. Okay? So the perimeter will include, in general, if I want you to calculate, if I ask you to calculate the perimeter of this one, let's say here I have W, here I have L. What will be the perimeter of this rectangle? So it will be W plus L plus W plus L. In general, the perimeter in Arabic in al-muhit. Okay? So the perimeter is the sum of the different edges of the form. But here, I need only this one, and this one. I don't need the whole perimeter of the junction. I need only the perimeter when I have junction between the N plus here and the P plus field implant. And this P plus field implant is not exist on the channel side. That's why, yes, correct, Monica. That's why here, what I need to calculate only this. I need to calculate only here this distance for J1. For J3, only here. For J2, this one is the perimeter that I need to calculate. Okay? Did you understand? Always you have to remove the channel side from the calculation of the perimeter. That's it. Keep it in mind. You have to memorize it. Once I need to calculate the perimeter of the junction, I need to remove the channel side from my calculation. Assuming lambda equals 0.2 micrometer. Find the area and the perimeter of the junctions J1, J2, and J3 for the circuit in the figure 2.16. يعني they mean this one. So here they told us that lambda, let me clean up here. They are telling us that assuming, sorry, here lambda equals 0.2 micrometer, they need us to calculate area of J1, the area of J2, 3, then the perimeter of J1, the perimeter of J2, and finally the perimeter of J3. Let me move this one a little bit in order to have some space. And let's move now to the calculation. Let me ask, for example, Haya. Haya, what is the perimeter of J1 equals what? Haya, can you hear me? Dana, can you hear me? Okay, Dana, please, I need to calculate. I need to calculate the area of the junction J1. What to do here? How to calculate the area? I just mentioned the formula to calculate the area. No answer, ya Dana? Let me ask Isa Hassan. Isa, can you hear me? Isa Hassan, can you hear me? Okay, please tell me how to calculate the area of the junction J1. Guys, this is not acceptable. This is really not acceptable. I just explained how to calculate the area of the junction and you told me you have no problem and you understood everything and now you don't know how to calculate. This is not acceptable at all. And you really disappointed me. Like I explained for nobody. Who know how to calculate the area of the junction J1 or you want me to just solve and move? The area of J1 equals what? Okay, Monica, go ahead. Okay, so it's equal to what here? Yes, correct. So here I can see it's equal to 5 lambda multiplied by what? So the distance from here to here is equal to. What about the distance from here to here? Why it's 9 lambda? It's 10, yeah, Monica. So it's 5 lambda multiplied by 9. Sorry. يعطيني يا Monica. So multiplied by 10 lambda equals what? Well, 5 lambda هي 5 multiplied by 0.2 يعني 1. 10 lambda is 10 multiplied by 0.2 equals 2. So the result here is 2. What is the unit in this case? The unit here is what? No? We have a problem here. The unit is micrometer squared, correct, Monica? Type. And the area of the junction J2. Well, regarding J2 here, I have two different parts. I have to divide it into two different parts because the form is not regular form. Yani it's not rectangle, it's not squared, it's not triangle. So we have here to find the area. So I can divide it into two parts. The first part is here, and the second part is here. Okay, so regarding the first part, the area is equal to 2 lambda multiplied by 10 lambda, صح? Here. Well, the second one is not really squared, approximately, plus the second one I have, well, I think I have to move the circuit here a little bit so you can see. No, there is nothing here. Oh yeah, nothing. Okay. Type. Plus what? I have from here to here 3 lambda, correct? In general, I have symmetrical here. And here, from here to here is 3 lambda. And from here to here is also 3 lambda. So it remains for this one what? 4 lambda, صح? Yani this rectangle is 3 lambda multiplied by 4 lambda. Plus 3 lambda multiplied by 4 lambda equals. So 2 lambda plus 10 lambda equals what? Or so 2 lambda multiplied by 10 lambda is 20 lambda plus 12 lambda. Is that correct? No, it's not correct. There is a mistake here. Where is the mistake here? So here it's 20 lambda squared plus 12 lambda squared. It's lambda multiplied by lambda. It's lambda squared. You have to pay attention to this point. Type equals what? 20 lambda plus 12 lambda. Well, 20 lambda حتكون 20 lambda squared. يعني 20 multiplied by 0.04. It's like 2 multiplied by 0.4 يعني 0.8 plus 12 lambda squared. So 12 times plus 0.08 يعني 0.48, correct? Equals 1.28 micrometer squared. What about the area of J3? Yes, it's equal to 2 lambda multiplied by 10 lambda. 2 lambda is 0.4 multiplied by 10 lambda is 2. 2 multiplied by 2 multiplied by 0.4 equals 0.8 micrometer, yeah, Monica, not millimeter. Micrometer square. Let's move now to the perimeters. The perimeter of J1, as I said, it's this one plus this one here plus this one here. We don't need to include the channel side. So the perimeter of J1 equals, I have here 5 lambda plus from here to here 10 lambda plus from here to here is 5 lambda. Yani equals 20 lambda, correct? 20 multiplied by 0.2, 10 by 0.2 is 2, يعني هون 4 micrometer, correct? Perimeter of J2, well, here it's a little bit more complicated because we have a lot of edges. So it's equal to 2 lambda plus 3 lambda plus 3 lambda plus 4 lambda plus 3 lambda plus 3 lambda plus 2 lambda. Correct? 2 plus 3 plus 3 plus 4 plus 3 plus 3 plus 2. Correct? Can 1, 2, 3, 4, 5, 6, 7 edges. 1, 2, 3, 4, 5, 6, 7. I think they are okay. So we have here 6 here and 4 is 10. 10 plus 2, 12. 12 and 2, 14. 14 and 6, 20. So it's the same as this one here. So 20 lambda, yani 4 micrometer. What about the perimeter of G3 equals what? I need an answer here. What is the perimeter of the junction? Yes, it's 2 lambda plus 2 lambda equals 4 lambda. 4 times 0.2, yani 0.8 micrometer. Any question here? Yes, correct. Perimeter, yes. P is a perimeter, correct, Adil. Saud Lanizi, is everything okay? Saud, can you hear me? Is everything okay, Saud? Okay. Here you have the answers. Don't forget that you have to pay attention always to the unit. Okay. Now the things start to be a little bit more complicated, so you have to pay attention to more parts. Here you can see another layout. In this case, sorry. Well, here they mentioned already that I have here this this gray here is P plus. This dark gray here is polysilicon. This one here is N plus. What else? The color here, this layer here, what you can see is the metal. So here I have metal. I will write inside. It's a metal. So I have metal here, and metal here. Correct? Then I have also here the dashed line here, the dashed area here is N-well. So here I can see N-well. Then you have the contacts here. They are like squared, and inside there is a cross. Correct? Is all the layers are correct? Can you see all the layers here? And the connection between the different layers? Is it clear for everybody? It's a little bit more complicated, but I think it's clear enough. Type. What you can see in this layout? What I taught you, well, Monica said, based on the poly, she can know. صح يا Monica? That's what you hear. But the poly is encountered with P plus or N plus, let's with active. What I mean by active is P plus or N plus. The poly here is encountered with active region only in this zone, صح? So here I have poly. From this side I have P plus. From this side I have P plus. So here I have PMOS. They already told you here I have P channel transistor, and here I have PMOS. And on the bottom here I have N plus, poly, N plus. And here also I have NMOS, correct? Yes. How they are connected? Can you see the connection between this NMOS and this PMOS? What is connected to what? Let me sketch them here. So first here, it's clear that I have here a PMOS. I don't know where is the source, where is the drain. Let's see that. And on the bottom here, I can see that I have NMOS. So Monica said that the polysilicon are connected. Yes, that's clear. The polysilicon for the PMOS is connected to the polysilicon for NMOS, and they formed what? They formed V input. So here, the poly here, the gate yani here, is connected to the gate here, and they formed what they called V input. But Adel and well will be inside the wafer, صح? So here, if you want, I can sketch cross-section view to show you what you are talking about. Okay? Please remind me by the end of this lecture, and in the 30 minutes after this lecture, to sketch to show you all the layers you are talking about. Type. What else? I can see that here I have contact and metal. So the N plus here is connected to the metal, صح? And the metal is connected to what? To the ground. So this layer here, this terminal, is connected to the ground. Did you see it? And if here I do a cross-section view, what I can see? If I do here, if I did here cross-section view, what I can see? Well, this is first I start the cross-section view from P substrate. Then I have N plus from here to here. I have N plus from here to here. Then I have P plus substrate tie. Well, it's not clear here, but they told us that it exists. So I have here also P plus. I have one contact here and one contact here. I have one contact here and one contact here. And then I have the metal is from here to the end. This is the metal. So I can see that the metal here is connected to this terminal. If you don't have the contact, even if you have metal, the metal will not be connected to the semiconductor. Is this point clear for everybody? Without the contact layer, the metal will not be connected to the semiconductor. Here we can see that the metal is connected to the semiconductor. So this terminal of the MOSFET is connected to the ground. Did you see this point? Good. So here, what you can see here, I can see that the metal is connected to this terminal, and it's also connected to this terminal of the PMOS. Yani this terminal is connected to this terminal. No, Monica. You have to memorize where is the each layer exists. Yani N plus is always inside the silicon, cannot be on the top of the silicon. Always you have the contact as a connection between the semiconductor and the metal. Always. Even if you see that it looks like in this layout that the contact is above the metal. No, forget. It depends on the method of sketching. Okay? Always you have the contact is between the semiconductor and the metal layer. We still have here this layer. We can see here clearly that this P plus is connected to a contact. Then I have metal. So I have this P plus is connected to the metal. Then to what? To VDD. So here I have VDD. So this one is the layout of what? This is the CMOS inverter. So you can see now that we can have many layouts for the same circuit. Depends on the design and on the architecture. But the architecture of the same circuit could be many layouts. Depends on the optimization of the area. Depends in some cases on the design, what I need to have here and why I do that. Okay, guys, so many parameters play a role here. And here you can see that the connection between the PMOS and the NMOS, we have also a metal connected to it, V out. So here I have V out. Guys, please take a minute to check the sketch done here. So I will repeat, this one is called layout. And this one is called what? Schematic circuit. Please take a minute to check the connection and the circuit. Let me know if you have any question. And let me know if you have some difficulties. Let me know if you have some points until now you don't understand how we do it, or you don't understand how we can think like that. Please, let's interact. Let's see what is your problem, what you are suffering from. Area optimization, we let me open the CAM again. So in order to have the area optimization, what we can do, we can create the MOSFET like that. Okay, like that. So here, let's see, this is the drain. We have multi-fingers for the drain and multi-fingers for the source. Okay, and you can do it like that. In this case, you can optimize the area taken by the transistor. Instead of having a very long transistor, you can have multi-figure transistor, can increase the width of the transistor without increasing the area. Why that? Because here we have something called common junction. So for example, this junction here is for this drain. It's also used for the source. The same junction is used at the same time for the drain. Sorry, here. This junction is for the Q1 for the MOSFET Q1. At the same time, it's for the MOSFET Q2. This junction is used for Q2 and Q3. If you did not see well the different layers here, I will try to help you. In general, we have N plus in this zone. Let me change the color to this one and increase a little bit the size. So here I have this region. No, sorry. So from here to here, I'm trying to sketch good area. Then from here to here, then from here to here. So I can say that we have N plus in this region. You can see here that you have metal on the top of N plus. That's why you cannot see N plus here. So all of this region is N plus. Of course, the polysilicon here will disactivate the N plus inside, the N plus under it. Okay, and here you have metal on the top of the N plus. That's why you cannot see N plus, and so on. Right. If I want to sketch now the MOSFETs here, how I sketch it? First, here I have a terminal, could be drain, could be source, I don't know. Then I have a gate. Then I have another terminal. Then I have a gate, another terminal, gate, another terminal, then gate, then another terminal. If you follow the metal here, you can see that all the polysilicons are connected together here, صح? And all the gates of these transistors are connected together. Did you see that? Did you see that all the gates are connected together? We can see also that this terminal here is connected to the one here, and it's connected to the one here. And you have this terminal and this terminal are connected together. So here, if which one in the top is the drain and the one on the bottom is the source, so this junction is the drain for Q1 and for Q2. Sorry, Q2 is here. And this junction is the drain for Q3 and Q4. This junction here is the source for Q1. The junction here is the source for Q2 and Q3. The junction here is the source of Q4. So you can sketch it as I did it here. So you can see it like that. You can see the connection. Also, you can sketch it like that. So here what you have to know, here you have to know that W total, so W for transistor is equal to W1 plus W2 plus W3 plus W4. So here it's like you have only one transistor with width equal the sum of the different transistors as they are connected. Okay, guys? So always when you see multi-finger MOSFET, you have to know that the width of this multi-finger MOSFET is equal to the sum of the different widths of the different parts or different MOSFETs inside, or let's say of different fingers. Yani here, let me clean up the circuit and talk a little bit about the width. You know that the width of Q1 is from here to here. This is W. So I will call it W1. Okay? So W total here is W1 plus W2 plus W3 plus W4. As I said, the area optimization is coming from I'm using mini junction as common junctions. So instead of having two junctions, one for Q1 and one for Q2, instead of having two junctions for the drain of Q1 and for the drain of Q2, I'm using only one junction. So in this way, I'm optimizing the area. The last example for today. So please, for next time, to make our lecture efficient and to profit from this lecture, because I'm going only to solve some questions, to show you examples, to do some review in order to not have any problem during the in-class assignment. Please try to repeat what we did today, what we have seen in the previous lecture, in order to help me, in order to understand better during the next lecture. In this layout, we have the blue color is the metal, the red color here is polysilicon. Can you see the yellow color here? So here I have yellow color. This is the limit. It's start from here and finished here. You have to know that, for example, here, this is the blue. Here I can see that I have blue and the yellow on top to each other. Okay? So here, this yellow color here is P plus. We have this layer here, the green is NOL. What else? You know that the white squared here are contact, okay? You see here the green rectangle. This is the limit of the green rectangle. The green rectangle here is N plus. Do you have any more layers? I think no. So you can see that I have P plus in the whole area here. But once I have polysilicon, what that means I don't. Okay, guys? Did you get this point? I need to repeat it. I will repeat. Here I have polysilicon P plus, but because of the polysilicon of P plus will not be weighted. And if I want to sketch here cross-section view, let's see if you can. This will be the last. I want to do cross-section view along this line. I can do it. I will start from, as I said, always I start from P minus substrate, and I have to write it here. P minus substrate. Starting from here, well, here the black color is the P substrate. Okay, Monica, let's start. From the beginning, what I have NOL. NOL is from where to where? NOL is from the beginning till the end, صح? All this region is covered with NOL. So guys, if you see some point not clear, you can stop me directly. So I have NOL from here till here. Here I have NOL. Then here, what I have here? I have P plus, correct. So the P plus is from here to here. I have to remove P plus only once I have what? The polysilicon, صح? So I have P plus from here to here, then from here to here, then from here to here. Correct? From here to here I have poly, and from here to here I have poly. Let me change the color for the poly. I will use the red. And here I have polysilicon. In your sketch, if you mention that the poly is like that, that means you know nothing. Because in this one, you don't have MOSFET. It's not acceptable to sketch the poly like that. The edge of the poly should be on the edge of what? The edge of the poly should be on the edge of the active region. So the poly is like that. Okay? And don't forget to sketch also the silicon oxide layer. So here is P plus, P plus, P plus. Here I have poly. And here I have poly. What else? I have two contacts, one here and one here. صح. I will use the black for the contact. The contact should be here and one contact here. What else? What else? The last layer. Yes, I do have metal from here to here in this region. I have metal here and metal here, صح? Around the contact. يعني here I have a metal and also here I have a metal. Done. That's it. So here and here I have metal. I will stop here today. As I said, please try to do some review. The different steps of the process you need. If you have any question, we can discuss any problem you have. You can do many examples. You can focus on some points that you see it's not clear for you. That's why it's needed to do some review before the next lecture. This is everything.